Imagine for a second that you could just completely strip away the sleek, polished glass of your smartphone screen.
Oh, that would be a mess.
Right, totally.
Yeah.
But I mean, imagine tearing down the colorful icons, the smooth animations, the perfectly designed interfaces of all your favorite apps.
Yeah.
And you're just staring at the raw, microscopic gears turning underneath it all.
It's kind of a dizzying thought.
Exactly. You wouldn't see photos or messages or videos. You would literally just see billions of tiny switches flipping on and off billions of times a second.
Yeah, and that's the part we almost never think about, right?
Right. We live our entire modern lives on these devices, yet, I mean, most of us have absolutely no idea what is actually happening beneath the surface.
And to be fair, that is entirely by design.
Oh, really?
Yeah, absolutely. I mean, we've built this entire digital universe on top of those switches, and it's specifically engineered to hide that staggering complexity from us.
Just because it would just be too much to handle.
Exactly. But the moment you start to look at how it all actually works, the illusion kind of fades. You realize it's not magic at all. It's just pure architecture.
And that is exactly our mission for this deep dive.
I love it.
We have a massive stack of technical blueprints, system architectures, and network protocol documentation to go through.
The fun stuff.
The very fun stuff. And our goal today is to extract the fundamental laws that govern this whole digital world. We want to shortcut the path to you being truly well-informed about the tech you use every day.
Which is so important right now.
It really is. So we're going to trace the journey of a single piece of information, starting from a microscopic flip of a hardware switch, moving through the logic of software algorithms, all the way to a global network spanning the Earth.
Okay, I am ready. Let's do this.
Okay, let's unpack this. Because before a computer can do anything, I mean literally anything, it has to understand the information we give it. And going through the documentation, there is one big umbrella term under which all the others reside. The concept that serves as the bedrock for everything else.
Ah, yes. Abstraction.
Yes, abstraction.
Abstraction is arguably the most powerful tool in all of computer science.
Really, the most powerful.
Oh, without a doubt. The primary purpose of abstraction in software design is simply reducing complexity.
Okay, reducing complexity. How?
Well, it works by focusing only on the most important, essential parts of a system, and it completely hides the irrelevant details from the user, or even from the programmer.
Huh.
What's fascinating here is that every single digital interaction you have is just a towering stack of abstractions built on top of ones and zeros.
You know, there was an analogy in the source material that made this click perfectly for me.
The oven analogy.
Yes, the oven analogy. Think about what happens when you want to bake cookies.
Okay, now I'm hungry.
Right. But seriously, you walk up to your oven, you set the temperature to 350 degrees, and you press the start button.
Yeah, simple enough.
That button is your interface. It's an abstraction. You don't need to know how to manually open the gas valve.
No, thankfully.
You don't need to know how to ignite the pilot light or regulate the internal fan to ensure even heat distribution or, I don't know, monitor the internal thermostat thousands of times a second to adjust the fuel flow.
Exactly. The start button completely hides all of that complex hardware logic.
And abstraction does the exact same thing for software design,
It
right?
does. It allows programmers to manage massive complexity without getting bogged down in the physical realities of the hardware.
Right, because if they had to think about every single electron,
Oh, it would be impossible. If a software developer had to write instructions for exactly which physical transistors should receive electricity every time you typed a single letter on your keyboard, they would never finish writing a single application.
wow, so they just build on top of what's already there.
Exactly. They rely on pre-built layers. A programmer writes a high-level command like display text, and the abstraction layers beneath that command translate it down.
Down into
Well, step by step, it goes into assembly language, then into machine code, until it finally becomes the literal electrical signals the hardware needs to illuminate the screen.
Okay, but if we peel back all those layers of abstraction,
Yeah,
if we bypass the high-level code in the operating system, we eventually hit the bottom, right?
you hit the bare metal.
The bare metal.
Yeah.
And that hardware only understands one thing. Binary. Just ones and zeros.
That's right.
So my question is, why? I mean, why are we still using a system of just ones and zeros when we have computers capable of rendering, photorealistic 3D worlds.
That's a great question.
Why not a more complex language?
Well, it really just comes down to the physical constraints of the hardware. Human beings use a base 10 number system, the decimal system.
Right, 0 through 9.
Exactly. And we use 10 digits, likely because we evolved with 10 fingers to count on.
Makes sense.
But computers don't have fingers.
No, they don't.
At their core, they are built out of billions of microscopic transistors. And a transistor is essentially just a switch that controls the flow of electricity.
Okay.
It can either let electricity pass through or block it. It has exactly two physical states, high voltage or low voltage, on or off.
Right.
Because the physical hardware only has two reliable states, the mathematical system we use to represent data must also be base 2. And that is binary.
So instead of powers of 10, the ones, tens, and hundreds, places we learned in grade school, binary uses powers of 2.
Correct. Reading from right to left, the place values in binary are 1, 2, 4, 8, 16, 32, 64, 128, and so on.
Every position is just double the previous one.
Exactly. And each of these positions is what we call a bit, which is simply short for binary digit.
Bit. Binary digit.
Okay. And just like in our decimal system, you determine the value of a number by adding up the place values that have a 1 in them.
Okay, let's walk through this mechanically, because seeing the math actually work strips away a lot of the mystery.
Sure, let's do some math.
Let's say we want to represent the decimal number 6 in binary language. How do we translate that using the place value method from the blueprints?
It is actually a really straightforward process of subtraction.
Okay.
You look at your binary place values. Let's look at a standard 8-bit sequence.
So that's 128, 64, 32, 16, 8, 4, 2, 1.
Perfect. You start from the left and find the largest power of 2 that is less than or equal to your target number. Our target is 6.
Right.
So what's the largest power of 2 that fits into 6 without going over?
Well, 8 is too big, so it has to be 4.
Exactly. So we place a 1 in the 4's place. That bit is flipped on.
Okay, so 4 switches on.
Now we subtract that 4 from our target of 6. 6 minus 4 leaves us with a remainder of 2.
Got it.
So we move to the next place, value to the right, which is the 2's place. Does 2 fit into our remainder of 2?
Yes, perfect.
So we put a 1 in the 2's place. 2 minus 2 is 0. We have nothing left to represent. So we put a 0 in the 1's place. And we put zeros in all the places to the left that we skipped, like the 8s and 16s.
So reading that sequence, the 4's place gets a 1, the 2's place gets a 1, and the 1's place gets a 0. That means the binary representation of the decimal number 6 is simply 0, 1, 0.
Precisely. You just turn on the 4 switch and turn on the 2 switch. 4 plus 2 equals 6.
Wow. It is incredibly elegant.
It really is. And the standard grouping of these bits in modern computing is 8 bits, which you call a byte.
Right, a byte.
With just 1 byte, 8 bits, you can represent 256 different values, from 0 all the way up to 255.
Just by flipping different combinations of those 8 switches.
Exactly.
And this is where the sheer scale of the system becomes apparent to me. Because we aren't just talking about doing basic math here.
No, not at all.
This simple system of binary switches scales up to represent literally everything on your computer. Text, images, sound, it's all just numbers in disguise.
It is. Take text, for example. Early computer scientists simply created a lookup table. They assigned a specific number to every letter.
Like the ASCII system, right?
Exactly. In ASCII, the capital letter A is assigned the decimal number 65. So when you type A on your keyboard, the computer doesn't see a letter. It stores the binary sequence for 65.
Which would be, let's see, a 64 and a 1. So 01, 00000001.
You got it. And that exact same principle extends perfectly to visual data. Images are broken down into a massive grid of tiny squares called pixels.
Right, everyone knows pixels.
But for a standard color image, each pixel simply stores 3 numbers: the intensity of red, the intensity of green, and the intensity of blue. The RGB color model.
Okay, so each color gets its own number.
Yep. And each of those 3 colors is typically assigned 1 byte of data, meaning it can have a value from 0 to 255.
So a specific shade of purple is just a specific mixture of red, green, and blue numbers.
All stored in binary. The higher the resolution of the image, meaning more pixels in the grid, the more bits you need, and the larger the file size becomes.
And sound works exactly the same way, right? The engineering notes detailed how sound is captured through a process called sampling.
Yes, sampling. The microphone measures the physical amplitude of a sound wave thousands of times a second.
And every single measurement is recorded as a number.
Exactly. String millions of those numbers together, and you have a song. It's all just sequences of ones and zeros hiding behind layers of abstraction.
But the architecture of digital files hides something else too. Because when you take a photograph with your smartphone, The device isn't just saving the grid of colored pixels.
No, it's doing a lot more than that.
It is automatically generating and embedding a secondary payload of information. This is what we call metadata.
Right.
What is the purpose of metadata, really? It's literally data about data, isn't it?
That's exactly what it is. The purpose of metadata in digital information is to describe the properties of the file without being the file's actual content.
Give me an example.
Sure. For a digital photograph, the metadata might include the exact date and time the photo was taken, the specific model of the camera or phone used, the lens aperture settings, and crucially, the precise GPS coordinates of where the device was located when the shutter was pressed.
I want to pause on that because the implications are massive.
Well, they are.
If someone takes a picture of their living room and sends it to a stranger on the internet, they probably assume they are just sending an image of a couch and a television.
Right.
But if that metadata is intact, they're essentially handing over their exact home address.
That is the mechanical reality of how these file structures work. If we connect this to the bigger picture, metadata is a massive privacy concern precisely because it is invisible to the user.
Yeah, you never see it unless you specifically go looking for it.
Exactly. When you upload a photo to certain social media platforms or send it directly as an email attachment, you are transmitting the EXIF data. That's the specific format for image metadata.
Okay.
And unless the platform's software is specifically programmed to strip that data out upon upload, you are broadcasting your geographical location and your daily routines. The abstraction layer hides the complexity, but it also hides the risk.
Okay, let's look at the sheer physics of this for a second.
Okay.
If every high-resolution photo has millions of pixels, and every single pixel requires 24 bits of binary data just to determine its color, plus all the hidden metadata.
It adds up fast.
And we are shooting 4K video at 60 frames a second and downloading massive software updates. We are generating a staggering volume of data. Why aren't our networks completely choked? Why don't our hard drives fill up the day we buy them?
They absolutely would if we stored all that data in its raw, uncompressed format.
Compression.
Yes. The solution to that bottleneck is data compression. Compression algorithms reduce file sizes by encoding the underlying information much more efficiently. And in system design, you constantly have to choose between two fundamental approaches to compression.
Lossy and lossless.
Exactly.
Let's break down the mechanics of those two approaches. Lossy compression gives us formats like JPEG for images or MP3 for audio files.
Right.
The documentation says it permanently removes data that human senses struggle to perceive. It literally just throws the data away. Is that right?
That's right. Lossy compression relies on the biological limitations of human perception.
Like what?
Well, it's a field known as psychoacoustics for audio, or psychophysics for visual data. In a photograph of a blue sky, there might be thousands of microscopic variations in the exact shade of blue.
Okay.
But the human eye cannot distinguish between shade number 142 and shade number 143. So, a lossy compression algorithm simply deletes all that nuanced data and replaces a large block of pixels with one uniform shade of blue.
Oh, wow.
The file size shrinks dramatically, but the original raw data is permanently destroyed. If you decompress a JPEG file, you are only viewing an approximation of the original image.
Wait, why not just use lossy compression for everything to save maximum space?
Mm.
If storage hardware is incredibly cheap today compared to 20 years ago, are we really throwing away data just to save a few megabytes on a photo?
We absolutely are, primarily because of transmission speed, not just storage.
Oh, right. Moving it across the internet.
Exactly. Moving a 100-megabyte raw photo across a wireless network takes time and bandwidth. Moving a 2-megabyte JPEG is nearly instantaneous.
Makes sense.
However, the destruction of data has cumulative consequences. If you take a JPEG, compress it, send it, download it, compress it again, and save it, you experience what is called generation loss. The approximation degrades every single cycle until the image becomes a blocky, artifact-filled mess.
Which we've all seen online. So that brings us to the alternative, lossless compression.
Right.
If I'm understanding this correctly, what is the primary advantage of lossless compression?
The primary advantage is that it allows for the exact, perfect reconstruction of the original data. It reduces the file size without losing a single bit of information.
But how is that mechanically possible? How do you shrink a file without taking anything out of it?
You do it by identifying and optimizing patterns. Think of it as a form of shorthand.
Okay, shorthand.
A classic algorithmic example is run-length encoding. Imagine you have a very simple digital image with a large, solid white background. In raw binary, the data for a row of those pixels might look like a long, repeating string. Let's use letters to simplify. Imagine the letter A represents a white pixel and B represents a black pixel.
Okay, got it.
Your raw data might be A, followed by B, B, B.
Okay, so that's 6 A's followed by 3 B's. That's 9 characters of data.
Exactly. Run length encoding scans that data, recognizes the repeating pattern, and instead of storing all 9 characters, it simply stores the count followed by the character. It records 6A3B.
Oh, wow. You've just reduced 9 units of data down to 4, saving more than half the space, but you haven't lost anything.
Exactly.
When the computer opens the file, it just reads 6 A's and perfectly reconstructs the original string.
Precisely. And that perfect reconstruction is an absolute non-negotiable requirement in many fields.
Like where?
Think about a medical MRI scan. If a hospital uses lossy compression on a brain scan to save server space, the algorithm might look at a tiny cluster of irregular pixels and decide, that's probably just visual noise. I'll delete it and smooth it out to save space. Yeah, that tiny cluster of pixels could be an early-stage tumor. Losing even a single bit of data is completely unacceptable in medical imaging.
That is terrifying to think about.
It is. The same principle applies to legal documents, financial ledgers, and executable software code. If you compress a software program using lossy compression, and it throws away a few lines of code it assumes are redundant, the program will instantly crash when you try to run it. Perfect fidelity is required.
Okay, so we've established how we represent the physical world in binary, how we hide the raw mechanics behind abstraction, how we attach hidden metadata, and how we compress it all down to move it efficiently.
We've covered a lot of ground.
We understand the static data, but data just sitting on a hard drive doesn't do anything.
Right.
How do we manipulate it? How do we make the machine actually perform work?
Oh.
This brings us to the logic layer, programming and algorithms.
This is where we transition from storing state to executing action. And what is remarkable about software architecture is that no matter how complex a piece of software is, whether it's the algorithm regulating a pacemaker or the physics engine of a massive 3D video game, all algorithms constructed using just 3 fundamental control structures.
The big 3.
The big 3: sequencing, selection, and iteration.
Let's pull these apart. First up is sequencing. What is the primary purpose of sequencing in programming?
Sequencing is the absolute baseline flow of any program. Its primary purpose is ensuring code executes exactly in the order it is written, line by line, strictly from top to bottom.
Give me an example of why that matters so much.
Well, if you write an algorithm to calculate an employee's weekly paycheck, the sequence matters. You must first multiply the hours worked by the hourly rate, calculate the taxes on that subtotal, and then subtract the taxes to get the final amount.
Okay.
If you reverse that sequence, if you try to subtract the taxes before you've calculated the gross pay, the logic completely breaks down. Sequencing guarantees the order of operations.
I see. But if a program only ever ran straight down from top to bottom, it would be a completely rigid script.
Right.
It would do the exact same thing every single time it ran, regardless of what the user did. It wouldn't be interactive.
Exactly.
That leads us to the second building block, selection. The classic Eiffel statement. What is the main advantage of using conditional statements?
The main advantage of conditional statements, or selection, is that they allow a program to branch. They change its flow and make decisions based on the specific data it receives in the moment.
So it's making a choice.
Yes. You provide the program with a Boolean condition, a mathematical statement that evaluates to either true or false. For example, if the user's account balance is greater than the purchase price, approve the transaction. ELSE, decline the transaction. Selection is the mechanism that gives software its dynamic, responsive behavior.
Okay, so sequencing provides the order, selection provides the decision-making. The third fundamental structure is iteration, loops.
Loops are where computers really shine.
Right, because the true advantage of a computer isn't just that it's smart. It's that it can execute incredibly boring, repetitive tasks millions of times a second without making a mistake.
Exactly. Iteration handles repetitive execution. But within software design, choosing the right type of loop is critical for efficiency.
Right. Which statement best describes the difference between while loops and for loops, for example?
Well, a for loop is ideal when you know exactly how many times you need to iterate. Like if you have a specific list of items, say an array of 50 student grades, and you want to add a curve to every single grade, you would use a for loop because it's ideal for iterating through arrays when the index is needed. It iterates exactly 50 times.
Okay.
But there is another control structure that is incredibly powerful when dealing with unpredictable user behavior.
And that is?
The while loop, or as it is often conceptually described, the repeat until structure. It allows a program to execute the same sequence of statements repeatedly while checking a condition.
Let's frame this with a real-world hypothetical. Suppose you and I are designing the login system for a new banking app.
Okay.
We need the user to create a password, and our security rules dictate it must be at least 12 characters long.
Sounds secure.
We don't know if the user is going to get it right on their first try or if they're going to try 5 different 10-character passwords first. So, to directly connect to our listeners, imagine you are asking a user for a password. Which control structure would be most appropriate for validating that user input where the exact number of repetitions is unknown?
You cannot use a standard for loop because you don't have a fixed number of iterations. You must use a control structure that checks a condition repeatedly while the outcome is unknown.
So the repeat until loop.
Exactly. A while loop or repeat until loop is perfect here. The algorithm essentially says, repeat the prompt asking for a password until the length of the input is greater than or equal to 12 characters. The program traps the user inside that loop, repeatedly executing the same sequence of instructions until the specific Boolean condition is finally met.
You know, it's funny, speaking of looping and iterating, a lot of students get tripped up on questions like, how many times will the value of I be printed when tracing code?
Oh, absolutely. Tracing loops manually is a huge part of learning programming. You have to follow the sequence exactly as the computer would to catch any errors.
Right, so those 3 structures, sequencing, selection, and iteration, are the atomic building blocks. But when you look at modern software, like an operating system, you are looking at millions of lines of code.
Yes, millions.
An individual programmer cannot possibly keep all of that logic in their head at once.
Yeah.
And they certainly don't write it as one massive, continuous scroll of text. How is it actually architected?
It is architected through the principle of modularity. This programming concept involves breaking problems into smaller sub-problems.
Okay. What is the primary advantage of modular programming?
The primary advantage is reusability and managing complexity. Instead of writing monolithic code, programmers write isolated, reusable blocks of logic called procedures or functions.
So if I'm building a physics engine and I need to calculate the trajectory of an object constantly, I don't write the complex math for a parabolic curve every single time an object is thrown.
No, that would be a nightmare.
Right. I write a discrete calculate trajectory procedure once, I give it a name, and then whenever I need that math, I just call the name of the procedure, yet another layer of abstraction.
Precisely. It is procedural abstraction. The programmer calling the procedure only needs to know what it outputs, not how the internal math works.
Okay.
But to make these procedures truly reusable, they need to be flexible. That is where parameters come in.
What is the purpose of parameters and functions?
Their purpose is to receive argument values at call time. They act as placeholder variables within the procedure's definition, passing specific data into these reusable modules.
Give me an example.
You don't want a procedure that only calculates the trajectory of an object thrown at exactly 45 degrees. You want a procedure that calculates the trajectory of an object thrown at angle x. The parameter is x, which allows you to pass different data into the same reusable module every time you use it.
Oh, and sometimes a procedure needs to remember something from the last time it was used, right? Which type of variable maintains its value between function calls?
That would be a static variable. It doesn't get wiped out when the function finishes running. It holds its state for the next time the function is called.
Here's where it gets really interesting. This modular approach, building tools that accept parameters and return results, this is exactly how APIs function, isn't it?
Yes, exactly.
What does API stand for in software development?
Application Programming Interface. APIs take modularity to a global scale. They provide pre-built libraries of code so developers don't have to reinvent the wheel.
So if you are developing a ride-sharing app, you do not launch your own satellites and write a global mapping and routing system from scratch.
No, you just use a mapping API. Your code simply passes your driver's GPS coordinates as parameters into the API's pre-built procedures, and their servers handle the staggeringly complex algorithms required to calculate the fastest route, returning the result to your app.
It's all just objects interacting with each other. Actually, speaking of that, which programming paradigm emphasizes objects and their interactions?
That is object-oriented programming, or OOP. It groups data and behaviors together into objects, which is another great way to manage complexity.
And contrast that with which programming paradigm emphasizes pure functions and immutable data.
Functional programming. It avoids changing state and mutable data, which can make debugging certain types of complex systems much easier.
Okay, so we have our sequences, our conditional selections, our iterative loops, all neatly organized into modular functions and APIs. We write the code, we hit compile, and it immediately breaks.
As it always does.
Which, let's be honest, is the universal experience of writing software. This introduces the concept of debugging. What is the purpose of debugging in software development?
Debugging is the systematic process of finding and fixing errors within a program. And in system architecture, we categorize these errors into distinct types because they break the system in entirely different ways.
Right.
The first and most basic is a syntax error. Which type of error prevents code from compiling successfully? That's a syntax error.
That's essentially a grammatical mistake in the codes.
Correct. Programming languages have incredibly strict rules. If you forget a closing parenthesis, if you misspell a variable name, or if you leave off a required semicolon, the compiler simply cannot translate your high-level code into binary. It throws a syntax error and refuses to build the program until you fix the typo.
Okay, so you find the missing semicolon, you fix it, the code compiles successfully, you run the program, it's processing data, and then suddenly, right in the middle of a task, it crashes and the window closes. What happened there?
That is a runtime error. The syntax was grammatically perfect, which is why the program was able to start executing. But during the execution sequence, the program attempted an operation that is mathematically or practically impossible.
Like what?
A common example is an algorithm that accidentally attempts to divide a number by 0 based on unpredictable user input. Or it tries to pull the 10th item from a data array that only contains 5 items. The hardware cannot perform the requested action, so the program panics and terminates abruptly.
That makes sense. But here is the scenario that terrifies me. What if the program runs perfectly, but the output is just wrong? Like, which type of error occurs when a program runs but produces incorrect results?
You have just described a logic error.
A logic error.
Logic errors are arguably the most insidious and dangerous type of bug because the system will not warn you that anything is wrong. A logic error occurs when the program runs without crashing, but produces incorrect results due to a flaw in the algorithm's design.
So the app tells me that my checking account balance is negative $4 million.
Exactly. The machine did exactly what you instructed it to do. The problem is that your instructions were flawed. Perhaps you accidentally typed a plus sign instead of a minus sign in the tax calculation. Perhaps your loop counted to 10 instead of 11. The computer lacks the context to know your true intent, so it happily executes the bad math at lightning speed.
Speaking of execution speed, as datasets grow from thousands of records to billions of records, the actual design of the algorithm starts to matter immensely, doesn't it?
Immensely.
If I write a program that searches a massive database of medical records, how do I ensure it finds the right file efficiently?
Efficiency is a massive subfield of computer science. When searching a database, the system architecture dictates the algorithm. Let's compare two approaches, linear search and binary search.
Okay.
Imagine you are looking for a specific patient's file in a completely unorganized, randomized stack of 1 million physical folders. A linear search means you look at the first folder, check the name, then check the second folder, then the third, sequentially, until you eventually find your target or hit the end of the stack.
It is simple, and it works on completely unsorted data.
Right. But if the file you want is at the very bottom of the stack, it takes 1 million individual operations to find it. In software terms, if that database had 1 billion entries, a linear search would be excruciatingly slow.
What is the alternative?
The highly efficient alternative is binary search. But there is a strict prerequisite. The data structure must already be sorted alphabetically, chronologically, or numerically.
Okay.
Binary search utilizes a powerful algorithmic approach known as divide and conquer. Instead of starting at the beginning, the algorithm jumps directly to the exact middle of the dataset. It checks that middle file. Is your target name alphabetically before or after this middle file?
Because the list is perfectly sorted, the moment I check the middle file, I know definitively which half of the dataset my target is in.
Exactly. And more importantly, you instantly know which half it is not in. So in a single operation, you discard 500,000 files. You then find the middle of the remaining half, check it, and discard another 250,000 files. You have the search space with every single step. A linear search of 1 million items might take 1 million steps. A binary search of a million items takes a maximum of about 20 steps.
It is an exponential leap in efficiency.
It is. And this same divide and conquer strategy is the backbone of efficient data sorting algorithms as well. Like, which sorting algorithm uses the divide and conquer strategy? That would be merge sort.
Right, which continuously splits a list in half, sorts the tiny pairs, and merges them back together.
Exactly. Now, sometimes you need instant access. Which data structure provides constant time access to elements?
Constant time access, meaning zero searching required.
Basically, yes. An algorithm that has a fixed number of steps regardless of input size is an O1 algorithm, and arrays or hash tables provide that constant time access. You just ask for index number 5, and it jumps straight there.
Before we move on from data structures, I saw some acronyms in the notes, like FIFO and LIFO.
Mm.
Which data structure follows the FIFO principle? First in, first out.
That is a queue, like people standing in line at a grocery store. The first person in the line is the first person served.
And which data structure follows the LIFO principle? Last in, first out.
That is a stack. Think of a stack of plates at a buffet. You add a plate to the top, and the next person takes from the top. The last plate added is the first one removed.
Which data structure is commonly used for implementing recursive algorithms?
The stack is used for recursion, keeping track of function calls as they nest deeper and deeper.
Oh, and one more. Which data structure provides efficient insertion and deletion operations?
That would be linked list. Because instead of shifting a massive array, you just change a couple of pointers to insert a new piece of data.
Okay, so as long as we write clever, highly optimized algorithms like binary search or merge sort, computers can eventually solve any mathematical problem we throw at them, right? It just comes down to writing the right sequence.
This raises an important question. What happens when a problem is so complex that an algorithm would take thousands of years to solve?
Wait, really? A problem that breaks a modern computer like that? Give me an example.
The most famous example is known as the traveling salesperson problem. Imagine a logistics company has a delivery driver who needs to visit 50 different cities across the country.
Yeah.
The goal is to find the absolute shortest possible route that visits every single city exactly once and returns to the starting point, minimizing fuel and time.
That sounds like something a GPS app does every day. Just calculate the distance between all the cities and pick the shortest path.
The difficulty lies in the sheer number of possible combinations. To definitively prove you have the absolute best, optimal route, the algorithm has to calculate every single possible path. With just 50 cities, the number of possible permutations is astronomically large, far greater than the number of atoms in the observable universe.
You're kidding.
I'm not. You simply cannot calculate every combination. It is a practically unsolvable problem using brute force calculation.
But logistics companies deliver packages every day, so if they can't calculate the perfect route, how do they generate a route at all? Do they just guess?
In a highly educated way, yes. Which algorithmic approach uses trial and error to find approximate solutions? It's called heuristics.
Heuristics.
When an exact, optimal solution is computationally impossible within a reasonable time frame, a heuristic approach sacrifices perfect accuracy for speed. It uses trial and error, educated guesses, and shortcut rules to find a solution that is good enough and highly useful.
So a heuristic algorithm might say, always go to the nearest unvisited city next. It won't give you the absolute mathematically perfect route, but it will give you a very good route in 3 milliseconds instead of 3 million years.
Exactly right.
That is fascinating. We literally have to program our precise, logical machines to make good enough guesses because reality is just too mathematically complex.
Yep.
And building these massive heuristic engines, these sorting algorithms, this isn't done by one person typing away in a basement. Modern software requires hundreds of engineers working simultaneously. How do they collaborate on millions of lines of code without constantly breaking each other's work?
They rely on strict structural oversight. What is the primary purpose of version control in software development?
Tracking changes, right?
Yes, tracking changes and allowing multiple authors to collaborate on a shared code base without overwriting each other's work. Systems like Git act as a meticulous historical ledger. It tracks every single addition, deletion, and modification to the code, logging exactly who made the change and at what timestamp.
So if an engineer accidentally introduces a massive logic error that completely crashes the payment processing module, the team doesn't have to manually rewrite the code to fix it.
Exactly. Version control provides an absolute safety net. If a catastrophic bug is merged into the main software, the team can simply look at the version control history and instantly roll the entire code base back to the state it was in yesterday before the bug existed. It encourages innovation because developers can experiment on parallel branches of the code without fear of destroying the core product.
Okay, let's take a breath and synthesize everything we've built so far.
It's a lot.
It is. We started with microscopic voltages, abstracting them into binary bits and bytes. We built data structures, compressing them to save space. We moved to the logic layer, using sequencing, selection, and iteration to build modular algorithms.
We covered the big three.
Right. We've debugged the runtime errors, optimized the efficiency with divide-and-conquer searches, utilized heuristics for impossible math, and coordinated our massive engineering team using version control. We have built a masterpiece of software.
But right now, all that incredible logic and data is just sitting locally on one physical hard drive.
Exactly. If this system is going to be useful, it needs to communicate. How does a massive database query executed on a server in Tokyo physically reach the smartphone in your hand in New York in milliseconds?
We need infrastructure.
Right. This brings us to the final layer: systems, networks, and security, the global infrastructure.
The internet is the ultimate triumph of abstraction. It is a global, decentralized system of interconnected computer networks. But it is vital to understand the physical and logical infrastructure that makes that communication possible.
How does data actually travel?
If you want to send a 1 gigabyte video file from Tokyo to New York, it does not travel across the undersea fiber optic cables as one continuous, unbroken stream of data.
Right, because if there was a slight disruption in the cable, the entire stream would fail.
Yeah.
And you'd have to start the gigabyte transfer all over again. So how does it actually travel?
It utilizes a fundamental transmission method called packet switching. Before the file ever leaves the server, the networking software chops that massive 1 gigabyte video into thousands of tiny, completely independent chunks of data called packets.
There's an analogy for this too, right?
Yes, the Lego analogy.
Yeah.
Imagine you wanted to mail an intricately built Lego castle to a friend across the country, but the post office only allowed you to use standard letter envelopes.
Okay.
You would have to dismantle the castle, place a few Lego bricks into each envelope, number every single envelope so your friend knows how to rebuild it, address them all to the same house, and drop them in the mail.
And once those thousands of envelopes are in the massive postal system, how do they actually navigate the millions of different possible roads to get to the destination?
In a computer network, those intersections are managed by routers. What is the purpose of a router in computer networks?
It directs traffic.
Exactly. Routers read packet addresses and forward them along the best path toward their destination. When a packet arrives at a router, the router consults a dynamic routing table and sends it on the most efficient available path.
And crucially, because the internet is highly interconnected, those packets do not have to take the same path.
No, they don't. If one fiber optic cable in Seattle goes offline, the routers instantly adapt and forward the remaining packets through an alternative path in Los Angeles. This dynamic routing is what makes the internet fault-tolerant.
You mentioned the router reads the destination address. In digital networks, we aren't talking about street names and zip codes. We are talking about IP addresses, correct? The Internet Protocol.
Yes. Every single physical device connected to the internet requires a unique numerical identifier, an IP address, so the routers know exactly where to deliver the packets.
But didn't we run out of those?
Yes. The history of IP addresses highlights a massive architectural oversight. The original routing system, known as IPv4, used a 32-bit address format. Mathematically, 32 bits can generate roughly 4.3 billion unique addresses.
Which, when they designed the architecture in the 1970s and 80s, probably seemed like a practically infinite number. They couldn't have predicted that one day people's refrigerators and light bulbs would need their own internet connections.
Precisely. With the explosion of mobile devices and the Internet of Things, the world literally exhausted that supply.
Address exhaustion.
Exactly.
Yeah.
What does IPv6 address the limitation of IPv4? It addresses that exact issue. To solve this hard physical limitation, engineers developed and deployed IPv6. It utilizes a 128-bit address space instead of 32-bit.
How much bigger is 128-bit, practically speaking?
It is astronomically larger. A 128-bit system provides 340 undecillion unique addresses.
I don't even know what an undecillion is.
It's 340 followed by 36 zeros. To put that in perspective, we could assign a unique IP address to every single atom on the surface of the Earth, and we still wouldn't even come close to running out. It is a permanent solution.
Okay, so the Internet Protocol, IP, gives us the address format, and it handles the physical routing of the packets across the globe. But I've read that IP is strictly a best effort delivery system.
It is.
It just throws the packets toward the destination.
Yeah.
It does not actually guarantee that your Lego bricks arrive. Packets can get dropped by overwhelmed routers, or they can arrive completely out of order. If my computer receives a video file missing half its packets, the file is corrupted. How do we ensure the data actually arrives perfectly intact?
We implement an additional protocol that operates right on top of IP. Which protocol ensures reliable data transfer across networks?
Oh, what does TCP stand for in networking?
Transmission Control Protocol. TCP is the protocol that ensures reliable data transfer.
So if IP is the fleet of mail trucks handling the physical routing, TCP is the tracking number system, the delivery signature, and the inventory checklist.
That is an excellent analogy. TCP manages the reliability of the connection. Before the sender transmits the packets, TCP slaps a sequence number on every single one. Packet 1, packet 2, packet 3.
Okay.
As those packets arrive in New York, the receiving computer's TCP software catches them and checks them off the list. If it receives packet 1, packet 2, and then suddenly receives packet 4, TCP realizes something is wrong.
It knows a piece of the Lego castle is missing.
Exactly. It immediately sends a message back to the server in Tokyo saying, I am missing packet 3, please retransmit it. Once every single packet is confirmed received, TCP reassembles them in perfect sequential order, reconstructs the original file, and hands it up to your media player. IP handles the journey, TCP handles the integrity.
I want to talk about how humans actually interact with this routing system. Because when I want to check my email or search for something, I absolutely do not type a massive 128-bit hexadecimal IPv6 address into my browser window.
No, nobody does that.
I type a domain name like google.com. How does my computer know where to send the packets if I only give it a word?
It relies on a global translation layer. What does DNS stand for in networking?
Domain name system.
Exactly. DNS translates human-readable domain names into IP addresses. Think of it as the Internet's decentralized phone book. Human brains are terrible at memorizing long strings of random numbers, but we are excellent at remembering semantic names.
Right.
When you type a domain name into your browser and hit enter, your computer essentially sends a silent flare up to a specialized DNS server. It asks, what is the exact numeric IP address associated with this human-readable name? The DNS server looks up the record, replies to your computer with the true IP address, and then your computer uses that numeric address to initiate the TCP connection and route the packets.
And once we have the IP address and we've established our reliable TCP connection with the server, how does the browser actually request the web page? What language are they speaking at the application level?
They communicate using HTTP.
What does HTTP stand for in web technology?
Hypertext Transfer Protocol, which protocol is used for transferring web pages over the internet. It's HTTP. Your web browser sends an HTTP GET request to the server, essentially saying, please send me the HTML file for your homepage. The server receives the request, packages the HTML file into packets, and sends it back.
But this brings up a massive security vulnerability.
Oh, big time.
If my HTTP GET request, say, a request containing my credit card number or my login password, is chopped into packets and bounced across 15 different routers owned by different internet service providers across the country, couldn't anyone monitoring one of those routers just read my packets as they fly by?
They absolutely could. On an open network, packets are just plain text data. Anyone with network sniffing software can intercept and read them.
So what does this all mean for our privacy?
It means securing the data layer is critical, and the primary tool for that is encryption. What is the term for converting data into an unreadable format to protect it? Encryption. It's the mathematical process of converting readable plain text data into an unreadable, scrambled format ciphertext to protect it from unauthorized interception.
So even if a bad actor captures my packets at a router in Chicago, all they see is mathematical gibberish.
Exactly. Modern web traffic protects itself by upgrading from standard HTTP to HTTPS, the S standing for secure. HTTPS encrypts the data using a cryptographic protocol like TLS.
How does it actually scramble it, though?
Well, there are two main types. Which encryption method uses the same key for both encoding and decoding? That's symmetric encryption. It's fast, but you have to safely share the key with the server.
Which is hard to do over an unsecure network.
Right. So which encryption method uses both public and private keys? That's asymmetric encryption. The server publicly shares a key that anyone can use to scramble data, but the data can only be unscrambled using a private key that never leaves the server. So your browser scrambles your credit card number with the public key, sends it across the chaotic internet, and even if it's intercepted, no one can read it except the server holding the private key.
But security isn't just about hiding the data. How do I know the server I am talking to is actually my bank and not a malicious server sitting in a basement pretending to be my bank to steal that encrypted credit card number?
That is the second pillar of TLS security, which security measure involves verifying user identity, authentication. Encryption hides the data, but authentication verifies the identity of the participants.
Okay, how does that work?
Before your browser ever sends that credit card number, the server must present a digital certificate. The certificate is issued by a trusted third-party authority and cryptographically proves that the server operating at that IP address legally represents the bank. It authenticates the endpoint.
Okay, so encryption and authentication protect my data while it is out there traversing the public internet. But what about protecting my actual computer or my company's internal network from malicious traffic trying to force its way in?
You mean malware?
Right. What is the term for unwanted programs that replicate themselves and spread to other computers?
Those are worms. And viruses do something similar by attaching to legitimate files. Oh, and what is the term for unwanted programs that appear legitimate but contain harmful code?
Trojan horses.
Exactly. So how do we keep the bad actors out of the local environment entirely? For that, you deploy a firewall. What is the purpose of a firewall in computer security?
It's essentially a digital bouncer at the door, right?
Yes. A firewall is a critical perimeter defense system. It continuously monitors every single packet trying to enter or leave your network. It inspects the packets against a strict, predefined set of security rules. If a packet is coming from a known malicious IP address, or if it is trying to access a restricted network port, the firewall simply drops the packet. It deletes it before it ever reaches your internal servers.
Okay, let's take a step back and look at the sheer scale of the journey we've just taken.
It's been a long trip.
We started at the absolute physical bottom, the microscopic high and low voltage flips of billions of transistors. We explored how the mathematical elegance of base 2 binary allows us to represent those physical states as ones and zeros. We saw how layers of abstraction group those bits into complex data text, RGB pixels, sampled audio, and how compression algorithms shrink that data down to manageable sizes.
Right.
Then we climbed up to the logic layer. We saw how software engineers use sequencing, conditional selection, and iterative loops to build the dynamic algorithms that run our world. We explored how modular procedures and APIs prevent us from reinventing the wheel, how we hunt down insidious logic errors, how we optimize searches with divide-and-conquer strategies, and how we rely on heuristics when the math becomes practically impossible.
And then the global infrastructure.
Yes. We traced how that logically processed data is dismantled into packets, routed through a fault-tolerant maze by IP, mathematically verified and reassembled by TCP, translated by the DNS phone book, and rigorously defended by public key encryption and perimeter firewalls.
It is, without exaggeration, one of the most breathtaking architectures ever constructed by human beings, and taking the time to understand these underlying mechanics is truly a modern superpower.
It really is.
We live in a society entirely mediated by screens. Understanding how a heuristic algorithm might introduce bias into a logistics network, recognizing the exact privacy implications of the metadata attached to your photos, or knowing why a logic error in a banking app is so difficult to catch, this knowledge elevates you. It transforms you from a passive, oblivious consumer of magical technology into an informed, critical citizen who understands the infrastructure of the modern world.
We've built this entire digital reality on layers and layers of abstraction. We've specifically designed our systems to hide the staggering complexity behind friendly icons, simple start buttons, and smooth APIs. But as our global infrastructure relies more and more heavily on opaque heuristics and automated generated code, we have to ask ourselves something. Are we risking a future where no single human mind actually understands how the entire machine works anymore? Next time you casually tap a glass screen to send a message across the world, ask yourself, what complex mathematical reality is this simple interface hiding from me today? Thanks for joining us on this deep dive. Keep questioning the systems around you.